All right, let's kind of wrap this up. But in wrapping it up, we want to hit some really important points. This is I've just sort of sketched out the spectrum of the sampled signal, again showing the red as the negative frequency is a complex conjugate of the positive frequencies, and then that's copied up to each multiple of f sub s. A couple things that we need to know, and some of this is just terminology. First, there's a frequency here at half the sample frequency. It's right there, fs over 2. We have a name for that. That's called the folding frequency, f sub f. Sometimes f sub fold if you really want to be long-winded about it, and that's fs over 2. Okay, that's called the folding frequency. Very easy thing for you to know, very important thing for you to know. And basically the idea is, if you were to just draw a little dotted line here and look at the magnitude spectrum, you'd see that you could, and if I could fold the paper right across that line, except for the complex conjugate part, I would get, it's got even symmetry about that line, so the images fold about this line. Okay, so it's called a folding frequency. Okay, so that's just terminology. Secondly, I'll just write this down. We can, this is very important, recover x of t exactly, maybe I better outline that in red because it's very important that you know that, from the sampled signal as follows. Now let me just say, we can recover the original signal exactly from the sampled signal. Okay, that means, and that's really an incredible thing. That says that I can go from something that looks like this, the sampled signal, I will be able to go to the original signal, something that looks like that. Even though I don't know what's going on in between samples, I claim that I'll be able to do this exactly, with some, some provisos and that kind of thing. And here's how we do it. We do this as follows. We use an analog. When I say analog, I mean continuous time low pass filter with cutoff frequency equal to the folding frequency. Okay, and if we really want to do it right, we'll use a gain of t. All right, let me circle that with some color, because this is stuff that's really important. It kind of makes the world we live in possible, that we can do this. All right, and the idea is, before I go down here, the reason we can do that is, remember that these things, like this thing here, it is the original spectrum but scaled by t. And I'm going to draw a little circle around that. That's what this is. It's exactly the original spectrum. Now we have all these high frequency noise things. Okay, these are just noise. How do we get rid of those things? Well, we're in continuous time, right? And so the easiest way to get rid of this is to apply a low pass filter. And guess what? If I set the cutoff frequency right there and put a low pass filter that does that, a low pass filter, my diagram's getting kind of messy, it's going to pass this thing. Oh, I keep hitting that the wrong button. It's going to pass this thing that I want, and then if I gain it by t, that'll cancel out that t, and it will block all of those guys. Okay, so I mean, if I sort of redrew this, you would see that what I'm talking about. I've got this, and I've got these high frequency images, and then I put a low pass filter on this. With cutoff frequency right there at fs over 2, it's going to totally get rid of all this stuff and pass this thing here and pass the original spectrum. And then if I give it a gain of t, right, and this thing is at 1 over t, we'll be able to reconstruct the original signal. Alright, so I hopefully that makes sense. It makes total sense in the frequency domain. In the time domain, the argument works, but it's a lot trickier. Well, this works. This sounds remarkable to me. It always struck me as being remarkable that we could go from there to there. I mean, what happens? We don't know what happens between samples. How can I say that I can perfectly reconstruct the original signal when I never even measured most of the signal? I just measure it at these intervals of t seconds. Okay, well, the restriction that makes this possible is as follows. Okay, this is the thing we really have to know. Supposing the bandwidth B, there's B right there, suppose B is greater than or equal to the folding frequency. Okay, if that's true, think about it. B is now going to be over there, and this thing is all these replicas are spreading out, so this point is going to be over there. I'll draw this out. It's going to be a problem. If this is true, we cannot recover x of t. Okay, let me draw what happens. Okay, we still have, so there's our picture, right? And this is B. But now I'm going to have, let's put fs here. I'm going to have, oops, let me do that again. I'm going to have something that looks like this. Oops. I get this overlap. So this is xs of f. Now, this is 0. Well, what does that mean when there's overlap? Remember, do I even have it on this slide? Remember that this thing, I guess I don't have it here. Okay. What this is a sum of all these triangles. And if you actually add these together, think about adding this point to this point and this point to this point. What we end up with is something that comes down that looks like this. If you add that line to that line, you get a straight line across. And we get a straight line across there, a straight line across there. So the actual spectrum kind of follows this red line here. Well, the actual spectrum now doesn't look so close to the original spectrum now, does it? If I apply a low pass filter to this at the folding frequency, there's the folding frequency. So now this is my low pass filter. what we're going to get is something that doesn't look so good. We're going to get something that comes down and then goes over like that and then comes down like that. So that's the recovered, the spectrum of the recovered signal. It's going to have the right amplitude. It's going to be okay in this region, but in this region and this region of the frequency spectrum, we have big distortion. And you can think if FS is even lower, there's even more overlap, and this area of distortion is even bigger. All right, this distortion is called aliasing. Aliasing is a big problem. I'm going to keep this as red ink because these are major points. This allows us to run our cell phones and everything. If we do things right, we can recover the signals that we've sampled, but if we do things wrong, we don't get that privilege. All right, aliasing can be prevented. Can be prevented if we choose the sampling rate greater than 2f max, or I'm using f max here, but in our case we were calling f max b, so you can say fs is greater than 2b. So that's the same thing as saying if I multiply this 2 over to that side, 2b. Okay, if fs is less than 2b, then we get aliasing, but we can prevent it. Aliasing, second major point is that aliasing can not be removed, can never be removed once it occurs. So you have to know this. This is really super important. The minimum sample rate I'm going to call it f sub n is 2 fs. This is called the Nyquist rate. Nyquist rate, after Harry Nyquist, the guy, one of the guys who came up with this. Shannon was the other guy who came up with this. We always sample at a rate bigger than the Nyquist rate. Not equal to, but bigger than the Nyquist rate. Always. Okay, to prevent aliasing distortion. And usually 10 to 20% above. Okay, because we don't have ideal, I'm showing these results for ideal low-pass filters. We don't really have the option of having ideal low-pass filters. This is called the Nyquist sampling theorem. Some people call it the Shannon-Nyquist theorem because Claude Shannon was the other guy who worked on this with Nyquist.